Greetings and welcome to the Science in Slippers, where we gently discuss the wonders of the cosmos and sleepy eyes. Whether you're covered in bed or simply settling in for the night, you're in the perfect location. This video is meant to assist you, whether you're watching it with your eyes half closed or wrapped up in a blanket on the couch. Relax, slow your breathing, and enter that peaceful transitional state between wakefulness and sleep. Now, before we set off to explore the hidden humming world beneath the crust of the Earth, I'd love to if you find yourself appreciating this peaceful area of research. Please consider clicking the like button as a tiny favor, or signing up so you don't miss any more bedtime discoveries. It truly aids in the development of this small channel, and additionally, if you're still conscious enough to leave a comment, I'd be quite grateful. I would like to know what time it is for you right now, and where in the world you are listening from now. I adore seeing. I sincerely hope that all of the drowsy scientists who are dispersed throughout time zones are listening to each other in silence. Although the video is calming enough to put you to sleep, there's always the chance that it could be too engaging if you remain up. At least you'll learn a little bit more about the odd and hardy creatures who reside far beneath our feet. When everything is taken into account, it's a fairly nice exchange for an hour of lost sleep. So take a big breath, let it go, and let's start our peaceful, gradual journey into the enigmatic realm beneath the Earth's. There is a universe beneath your feet right now that you hardly ever consider. It's more than just rock and soil. It's a tiered planetary architecture marvel that descends thousands of kilometers at a time. More enigmatic and dramatic than the last. We're heading downhill tonight. Don't worry, it won't be too quick. We'll travel through regions of the Earth's strata where the pressure is so great that submarines might be crushed, and although it's not exactly a spa down there, certain things manage to survive there, despite the heat that could boil steel. Let's start with the portion of Earth's outermost shell that we are most familiar with. Is called the crust, and it is shockingly thin. When peeling an apple, the skin is the crust on land, which is typically 30 to 50 kilometers thick beneath the oceans, can be as thin as 5 kilometers, which is essentially the difference between a subway ride and a hiking route. All known surface life, including you and I, has evolved on this delicate crust. Where we have infrequently, the crust is composed primarily of igneous rocks, such as basalt and granite floats, when combined with sedimentary layers and fragments of metamorphic rock. Like crackers on a hot, gooey cheese dip, it rests ever so delicately on the mantle underneath it. Leading to our next. In order to enter the mantle, you must first break through the crust. Extends to almost 2,900 kilometers below the surface. That's a significant drop, so let's take your time. The mantle is divided into the upper and bottom layers. The top portion of the mantle is partially molten and travels very slowly, which causes the tectonic plates above to move, which is what drives volcanic eruptions, earthquakes, and the gradual shifting of continents. Hence, you can give credit to the upper mantle for Pangaea and Iceland's position atop a volcanic hot area that becomes hotter and more pressured. As you go more into the mantle, the temperature is considerably above 2,000 at a distance of about 1,000 kilometers, and the pressure is sufficient to make a diamond seem a little strained. Interestingly, the lower mantle remains fairly solid in spite of the heat, because of the V. Rocks here behave plastically like extremely rigid putty, moving at a velocity that locks everything in place because to the tremendous pressure of roughly a couple of centimeters annually. If you've ever seen paint dry, congrats. You've just replicated the lower mantle's pace, after which the core begins to deteriorate dramatic. Now, the outer core starts at around 2,900 kilometers below the surface and reaches 550 kilometers. This layer is primarily made up of nickel and liquid iron. It's not only it despite being a whirling dynamic sea of molten metal. The hot puddle is what's causing something quite significant: Earth's magnetic field, which subtly protects humans from, because the liquid outer core spins and convects. There is lethal cosmic radiation, generating electric currents, which in turn generate the geomagnetic field that directs migratory birds, makes compasses marginally more helpful than simply staring at the sun, and protects astronauts. If we continue, we will eventually reach the inner core, a solid, compact ball of nickel and iron, situated directly in the temperature here might reach 371 kilometers from the Earth's center, up to around 100 C, which is about as hot as the sun's surface. But the pressure is so high, more than 3 million times the sea level pressure, that iron stays solid, in spite of the heat within, even if we discuss it. Core doesn't melt. It's like attempting to cook a pot of soup inside a hydraulic press. These layers resemble discrete zones, but the boundaries are hazy, because Earth isn't stacked like a cake that can be sliced with a knife. Shock waves are sent through these levels by dynamic, ever-changing earthquakes, and by examining how those similar to utilizing ultrasound on a planet. Waves allow scientists to map the invisible structure beneath us. So where it turns out that life does fit into this geological lasagna, unexpectedly comfortable and certain of these settings, the crust, particularly the deeper regions, is home to something called the deep biosphere, is where microorganisms survive in lonely, dark rock. If you're a microorganism that lives in fish, surrounded by minerals and fluids that are rich in hydrogen, sulfur, and other delicious components, some of them live so far below the surface that they may be completely alone for millions of years. Without sunshine or fresh air, these microbial pioneers thrive, and many of them do so under crushing pressure. Instead of using sunlight to create energy, chemosynthesis uses chemical reactions. Because these creatures live so slowly, photosynthesis is like a gritty underworld relative of what plants do. Among the most patient life forms on Earth, some may only split once per 1,000 years. Scientists have discovered bacteria that live more than 5 kilometers below the surface, although the precise lowest limit of life is still unknown. In locations with temperatures above 120 C, which is hot enough to kill the majority of things on the outside. But because their proteins and membranes are heat adapted, these tiny champs simply keep reproducing, metabolizing, and being fantastic. But in a fascinating twist, we've hardly touched the surface of what lies beneath. According to some scientists, the deep biosphere's biomass could surpass the sum of all surface life, which is an astounding idea. The next time you go on a walk, remember that there is more stuff concealed in the rocks beneath us than in all the forests, oceans, and meadows above. Outside, keep in mind that the Earth is more than just a rock beneath your feet. If you look closely, you'll see that it's covered with wonder, buzzing with energy, and teeming with life that doesn't require light to it. Serves as a reminder that life finds a way, and does so even in the most gloomy, heated, and stressful environments. Deep beneath our feet, where there has never been any sunlight, and the air is more fantasy than recollection, it happens very slowly. Our tiny, resilient, and healthy organisms, if you believed, let me present you to the real deal. Penguins in Antarctica, or fish at the Mariana Trench's bottom, were extreme. The deep dwellers, the heavyweights of the survival game, are organisms that not only survive in harsh settings, but also toss house parties in them. So let's start with the show's stars, the so-called extrophiles, who are all extreme loves, are living things, primarily microbes, that have, in addition to adapting to environments that would kill nearly anything else. Imagine if you could only live in a sauna. That's also under a waterfall. In many situations, they need certain conditions to survive. Mountain and filled with poisonous fumes, and you enjoyed it that way. Extrophiles come in a variety of forms, tailored for a specific kind of extreme. Thermophiles, such as those who adore heat, not just warm heat, mind you. These creatures can be found in temperatures above 60 C, and frequently considerably higher. Deep underground, you got it, are hot springs in deep sea, hydrothermal vents, where the heat from the Earth's interior generates their own private sauna heaven. And then there are Greek pastophiles, These animals flourish in crushing environments, such as those found kilometer below the Earth's crust, and their name is pisces, which means pressure, or image, living beneath the weight of hundreds of elephants at the ocean's bottom. Not just being okay with it's a mouthful, but the chemolythroofs are a group of people who need it to feel comfortable. Detailed work description for a self-employed chemo for chemical litho, for rock auto with trough for feeder. They actually use chemicals from rocks to feed themselves. Sunlight. They may obtain energy from elements like hydrogen, sulfur, iron, and ammonia without the need for organic stuff. In essence, they believe that these organisms are important participants in what scientists refer to as the deep biosphere, is a massive, largely invisible ecosystem that could be responsible for a significant amount of Earth's life, although estimates differ. Some scientists think that up to 70% of all microbiological life on Earth is found underground, buried in rock, and conducting its extraordinarily sluggish, yet remarkably steady business. Now, if you're in contrast to plants, which use chemosynthesis to transform sunlight into energy, they rely on chemosynthesis to exist without it. Through photosynthesis, these microorganisms convert carbon dioxide into energy. For instance, they might turn iron compounds into useful energy, or oxidize hydrogen gas generated by radioactive decay in rocks. One of the most intriguing environments for these subterranean microorganisms is similar to solar electricity, but with a pickaxe and a hard hat, is found in deep crusto fissures and crevices in rocks like granite and basalt, which are not sturdy strongholds. These minuscule spaces, which are tiny fractures and pockets filled with fluid, develop into microbial condos. Yes, life moves slowly, but some microorganisms are remarkably persistent and can produce both tilms, even in times of food scarcity and environmental extremes. Communities held together by a slimy matrix stay safe and hydrated. Are severe. A large number of these organisms are anaerobic, which means they don't require oxygen. In fact, oxygen is poisonous to some people instead, depending on additional electron acceptors, such as carbon dioxide or nitrate sulfate, are organisms that contradict our beliefs about the conditions necessary for life to exist. Light. Nope. Air. Nope. A rock smaller than a sugar cube will provide them with the room they need to live. One of the most intriguing aspects of these deep-dwelling microorganisms is their slow rate of life. And I don't just mean relaxed, that is, they function on temporal scales that make glaciers appear swift, some of them dividing only once per few. Their extremely conservative energy budget allows them to maintain a slow metabolism for hundreds or possibly thousands of years. It's a never-ending shuffle, rather than a sprint or marathon. Yet given their surroundings, these sluggish metabolisms there are many species in the deep biosphere that don't do anything, which is one reason why scientists believe it to be so large. The microbiological counterpart of either dying or simply surviving for a very long time is, after spending 3,000 years in your cellar with just one granola bar and somehow failing to complete it, since we can't precisely use a petri dish to descend down 5 kilometers below the surface. You may be wondering how we know all of this. Using a dish and a spotlight. Researchers examine these species by drilling cores from deep boreholes, mine shafts, and one of the most ambitious scientific expeditions is the Deep Carbon Observatory, which has been in progress for years, investigating the deep Earth's carbon cycle and the life that depends on it. Researchers have discovered viable microorganisms, even in habitats, after recovering samples from kiln below the surface. Some of the inhabitants of the deep biosphere, which were previously believed to be entirely sterile, are so unusual that they have never been. They might appear as whole new branches on the tree of life when viewed from the outside. Ones that developed in these species may have been isolated for hundreds of millions of years and have never come into contact with sunlight. They're relatives from the dinosaur era, or perhaps older, and some microorganisms to keep things interesting have been discovered, consuming radioactive decay. Certain bacteria do indeed survive on the energy generated by, although the energy of radioactive elements in rocks isn't very high, it seems to be sufficient. They are similar to the microbial world's reactor. Custodians are silently working in the most remote and dark areas of the world. So when you envision life on Earth, don't limit yourself to images of forests, seas, and birds flapping their wings. Consider the microorganisms that live miles below the surface, adhering to the edges of rocks and consuming gases and minerals. They may be small and slow, but they are passing through time with the patience of stone. However, they are some of the world's most amazing survivors, and they serve as a reminder that every life, no matter how tiny, has an amazing ability to appear in the most unlikely locations at the furthest regions of the planet, away from the clamor. And one of the most bizarre discoveries in the history of biology was made by scientists using sunlight from the surface of the Earth. But they weren't drilling through ancient rock in the name of mining and science while searching for life deep within a South African nearly 3 kilometers below the surface of the gold mine. They discovered something surprising. Life is a solitary organism surviving in a hot, dark place by itself. Her name is the name of the planet where nobody thought anything could endure. It's a mouthful, Candidatus, Dularutus, or Dax Vita, but please be patient with me, because first, let's establish the scene. The mine in question is the Impan gold mine. This tiny bacterium has earned every sentence. One of the world's deepest man-made holes is located in South Africa. It's so deep that the rock's temperature can exceed C, which is hot enough to cause the wall to perspire. Ice must be used to cool the miners. Slurry to continue operating. The air is thin, the pressure is high, and yet, in a Desilarudis ord isn't just ordinary microbe. Researchers discovered something living in a tiny water-filled fissure in the rock. The sole species residing in that specific habitat, without any community, is what scientists refer to as a food chain, sunlight, photosynthesis, other microorganisms, and oxygen. Just one, Odax, is the name of an old, closed-off world, where a single species survives. Vieta, which means bold traveler in Latin, is a reference to Jules Verne's book Journey to the Center of the Earth, where the words descend orax vitor, or descend bold traveler, are inscribed. Since Dolphurus is as daring as microscopic life gets this small, is there really a better name? Sulfate reduction is the chemical process by which organisms survive. It uses energy to break down sulfate, chemicals in the nearby rock that need hydrogen as a fuel source. This hydrogen is produced by radializing water that is made up of water molecules that are being separated by natural radiation from potassium and uranium thorium in the tucked away in a crevice in the earth. Rock is a sort of new metabolism. The incredible thing is that nothing from the surface, nothing from photosynthesis, nothing from plants, or anything else is necessary for life. Animals are a completely self-sufficient system that is fueled by radiation, water, and rock. If extraterrestrials arrived on Earth and in 2008, when scientists were asked to view the most autonomous life form we have, this would be a serious contender. When the genome of Desilarus was sequenced, they discovered that it had almost everything they needed to exist on its own genes, for DNA repair, hydrogen and sulfate metabolism, and resistance to high temperatures and heavy metals in a single-celled body, making it a biochemical Swiss Army knife. Aside from the whole living alone at the bottom of the world thing, this discovery is really exciting because it reveals information about life in general, whether an organism can endure in total isolation without receiving any biological input from the surface. What does that signify for life elsewhere? It drastically changes the objectives for decades of researchers. People that are looking for extraterrestrial life have turned to Mars, Europa, one of Jupiter's moons, and the orbiting planet Enceladus. Saturn is a harsh, frigid planet by our standards. but it also has energy sources, and rock water seem familiar. But it turns out you don't need the astrobiology poster child, Desilorudis, has shown that all it takes is chemistry and time to sustain life in a sunny meadow. The study of life in the universe demonstrates that microorganisms require little to exist, which poses the potential that life, albeit not the kind we're used to, is abundant in the universe. Let's now take a moment to recognize how amazing it is that we discovered this organism at all. It wasn't a part of a large-scale expedition. Exploring the deep biosphere was more of a fortunate accident, brought about by mining activities and inquisitive scientists who are adept in posing strange queries, such as what's living inside this boiling rock. This fortuitous meeting has increased awareness of how diverse and unique Earth's interior ecosystems actually are. The planet appears to have been concealing secrets by hiding small, hardy organisms under its crust, such as tiny time capsules. And what else may be if Disilis is present? Ecosystems may be flourishing in remote areas of the planet that are totally shut off from sunlight. Over millions of years, some may be flourishing in old aquifers, while others may be tucked away in continental fissures or deep marine vents. Zones. We can be unaware of huge microbial metropolises subtly humming beneath our feet. Even though Disilaris is still a lonesome figure, his story is sufficient, since it teaches us that life doesn't merely adjust. It perseveres, survives, and discovers ways to live not only in difficult situations, but also in that appear completely uninhabitable. And it accomplishes this with no fanfare or fuss, just a tiny bacteria deep beneath, doing its thing. So keep in mind that somewhere 3 kilometers below the surface, the next time you're strolling around looking at the Earth, on the surface of the Earth, a brave microscopic wanderer leads a peaceful, nuclear-powered life, in the dark, and if deep underground, where sunshine has never reached. It's at least quite chilly for bedtime, even if it's not inspirational. Silence is essential, and life is managed to not only survive, but also establish a home. I mean living inside the rocks themselves, not just relaxing in warm caverns or hot springs. Nestled in areas smaller than a human hair's width, flourishing in the smallest pores and fissures. This is the domain of the living rock, where microorganisms refer to solid stone as their home. If you believed the apartment was little. To put it another way, picture living your entire life in a tiny bubble of water that is imprisoned in a grain of sand. The rocks, or Earth's crust, must be discussed first, in order to understand how anything might survive there. Many types of igneous and metamorphic rocks make up the oceanic and deep continental crusts in particular. At first appearance, basalt granite and other similar rocks appear to be inert and lifeless. However, when viewed under a microscope, they display a hidden architecture of mineral surfaces, pores, and Despite their small size, bacteria have the ability to store water, and life tends to follow them wherever there is water on Earth. These organisms live within stone, not on it, and are referred to as endoliths, the outside of rocks, but within them, in tiny water pockets, or along mineral surfaces. The rock is more than just it serves as both a pantry and a shelter. And many of these microorganisms obtain energy by interacting with, for instance, some minerals in the rock itself need iron, sulfur, or even manganese in their metabolism. To obtain energy, bacteria convert the ferrous ion Fe2 to the ferric ion F3+. Other chemical processes that convert sulfate to hydrogen sulfide may not seem interesting. But in the world of microbes, they're like preparing a substantial crust. The sluggish pace of life in the crust is one of its most intriguing features. These microorganisms are incapable of reproducing. In certain regions of the deep biosphere, a single microbial cell may replicate the surface-dwelling cousins in hours. The fact that some microorganisms only split once per few hundred, or even thousands of years, indicates that they have existed since prior to agriculture. They would simply hang out in their mineral nooks and crannies, slowly using chemical energy. Since deep rock habitats are low-energy systems with limited food supplies, why are they so slow? Microbes that exist in harsh settings with little space to develop. High pressure, high temperatures, and limited nutrition, they must be efficient. Role models because their growth techniques are patient and their metabolisms are simple. It's completely plausible that some of these creatures are suspended in geological time, living in a sort of ultra-slow motion. Although they move slowly, these microorganisms that live in rocks are far from inconsequential. According to experts, they are essential to Earth's biogeochemical cycles, which are the mechanisms that transfer elements, like carbon, sulfur, and nitrogen, are transported by deep microorganisms through the planet's processes. Whether rocks can store carbon over time and recycle nutrients, they function in the background unseen, much like Earth's silent maintenance crew. Keeping the as planetary machinery functions properly, biofilms are formed that are in the deep biosphere. Biofilms, communities of microorganisms bound together by a protective matrix, help bacteria adhere to. Rock surfaces can even create slimy coatings on the walls of deep caves, because they retain nutrients and withstand extreme weather. Another intriguing aspect of cracks is their ability to serve as little microbial civilizations with structure. The symbiotic interactions that can develop between certain bacteria and their environment are what give the crust its life. Cooperation may be necessary to break down minerals or nutrients that neither could handle on their own in these microscopic rock pores. The ultimate in survival is that one species' waste could become another's dinner. Microbiological recycling. But if you dig more, what about the circumstances? Pressure rises sharply, increasing by almost 1,000 times for every 10 kilometers of descent. Temperatures also rise, sometimes surpassing 120 days for the majority of the surface. Species that would be fatal, but the deep-sea microorganisms are suited to survive in these harsh conditions. Some have particular cell membranes that stay intact in the heat, while others contain heat-resistant proteins that don't unravel. Their DNA repair systems are resilient and steady under stress. The sporadic radiation explosions caused by naturally occurring disintegrating rock elements. These are not only survivors, they're experts developed over billions of years to withstand circumstances that appear completely hostile. And despite the best efforts, they are still mostly undetectable. Because of technology, scientists had to utilize specialized drilling to sample the deep crust without polluting it. Equipment and extremely hygienic methods to guarantee that they're not only identifying surface bacteria that snuck onto the drill bit. It's laborious work, but the every new sample, an unexpected genome, adds a piece to the jigsaw of Earth's history, making findings worthwhile. Deep biosphere, and the mystery surrounding certain microorganisms, keeps becoming more fascinating. Found in deep rock samples have genes with functions that are not closely related to those found on the surface. Although scientists are still learning a lot, there is a growing perception that the deep biosphere is more than merely an extension of above it. Life exists in a distinct realm with its own evolutionary pathways. Further poses intriguing queries, such as how long life has been inside the crust, and whether it may have started there. Some scientists suggest that early Earth would have been extremely hostile due to meteor and UV radiation bombardment. That it's possible that life began underground, shielded by rock, and was gradually nourished by chemical gradients. On the surface, it's a sobering realization, because although we often imagine life as something that the next time you pick up a pebble, think about how the initial spark might have shone in the dark, and then flourished in the light. May have had a flourishing microbial ecosystem in the past, and it may still be. Life isn't always what we expect it to be. Sometimes it's secluded, slow, stubborn, and constant, demonstrating that life can exist in even the toughest stone beneath our oceans, beneath our continents. And deep within the Earth's, there is something amazing beneath the mantilla, hidden ocean rather than a huge splashing sea. Similar to the Atlantic or Pacific, but a world of water that is soaked into minute minerals and trapped in rock pockets in the mantle and crust. And although it might not be a swimming-friendly ocean, it might have more. Let's begin with what we typically think of when we say water, which is more than all the surface oceans combined. The seas we know and love make up only a small portion of our planet's surface. Overall, they occupy over 70% of the around 1.4 billion kilometers of water on Earth's surface, which is a significant amount of liquid. But as it turns out, the Earth is quite greedy and stores water in surprising deep places. Some minerals have the ability to trap water molecules inside their surfaces to depths of hundreds of kilometers. Crystal structures, there are no subterranean lakes swirling around down there, so this isn't free-flowing water. This is bonded water with hydrogen and oxygen atoms held in place of lost aquariums. One of the main participants in this deep hydration drama is a mineral that is securely contained within the minerals themselves. Ringwoodite is a hyperpure version of olivine, a mineral that is frequently found in the upper mantle of the Earth, only appears at extremely deep depths, roughly 5 to 25 to 6 kilometers below the surface, at what geologists refer to as the mantle's transition zone, where temperature and pressure the circumstances are ideal for this mineral to function as a sponge. In 2014, researchers discovered an astounding discovery. They discovered a diamond with a tiny ringwoodite inclusion that had formed deep within the soil. The fact that the ringwoodite piece contained water, not just drops, but real hydroxide ions, was even more astounding. Crystal lattice provided concrete proof that the Earth's mantle might contain enormous volumes of solid water. Although estimates differ, some scientists believe that the mantle's transition zone alone may support up to 3 times the volume of water present in all of Earth's oceans, which is an incredible potential. This underground ocean, which has more water inside the Earth than on its surface, is more than simply a curious geological footnote. It plays a water reduces the melting point of rock, which is crucial for plate tectonics, volcanism, and even the carbon cycle. This facilitates the creation of magma at subduction zones, as tectonic plates plunge into the mantle. They carry minerals, and when these minerals cool and descend, they release water, which results in volcanoes frequently form above ground because the surrounding rock melts and forms magma. Water in subduction zones is discreetly fueling the geological fires below the surface by acting as a catalyst, but not only descends, but also rises over millions of years. The water that was through volcanic eruptions and hydrothermal vents, the mantle that has been locked away, rises to the surface, allowing Earth's in addition to flowing through rivers, clouds, and seas. Water is continuously cycling deep inside the planet's crust. The planet's mantle is a large, slowly moving mechanism that helps control its temperature and maintains the surface habitable. Now because life frequently exists where there is water, and the deep Earth is no different because hydrated rocks form. Microscopic, these concealed water pockets act as habitats for the deep and provide steady conditions for extraphile bacteria to flourish. Biosphere, which provides chemical nutrients, moisture, and in certain situations, protection. Water in the deep crust may actually be protected from radiation and other surface hazards. One of the most crucial sources of subsurface microbiological life, in locations such as the mines in South Africa's Canadian Shield, and researchers studying Finnish bedrock have found ancient groundwater that has been isolated for millions or perhaps even though some of these water pockets are billions of years old, they existed before the dinosaurs. They continue to sustain these ancient waters. Microbial life is abundant in hydrogen and other chemical energy sources produced by the water's interaction with the nearby rock. In a natural chemistry lab, and the microorganisms that reside there, they have adapted to slow-growing longeves and metabolically conservative. Some of these species are sufficiently adapted to their habitats that they can survive in these timeless settings. According to scientists, these could represent whole new life forms that are being studied. Not only are we learning about Earth, but we are also getting a glimpse of what life might be like in other parts of the universe. One of the most fascinating features of the Earth's hidden ocean is its location, where sunlight never shines. It doesn't only explain geology to us, it provides a model for astrobiology. If the Earth can conceal an ocean in its mantle, why not? Even stony planets may have subterranean oceans, as is the case with other planets' moons, like Europa and Enceladus. If life can flourish within the rocks of Earth, then Mars may contain hydrated minerals deep down. Repeat the same elsewhere. Here at home, we're only now realizing how much of our reality is influenced by this. Internal water, every mountain, every tectonic movement, and every volcanic eruption. It's easy to forget that range is partially responsible for its existence, due to the subtle influence of water flowing beneath the surface. Seeing how fluid our globe is when standing on firm ground, you lie back and lose yourself in thought about the water you are familiar with. The rain drumming on your roof, the rivers meandering across the landscape. Consider the water hidden inside crystal structures as you watch the waves crashing into the coast, silently sculpting the soil from within while slowly floating through old rock, because there is another ocean. A secret one, beneath the towns, woods, mountains, and oceans. Time is a curious thing in the deep dirt of the planet, where life stirs, in its silent depths. On the surface, we commemorate its passage with sunrises, sunsets, seasons, birthdays, and teacups that have been forgotten. But below, time is completely different way. Below, it's patient and slow. When we question how long life is, even bacteria down there measure it in millennia rather than hours or days. Has existed beneath the surface of the Earth, and we are entering a new era of time that is not based on clocks. But in order to comprehend the age of deep-earth life, we must examine the fossil record rather than the type with the fossils we are discussing, such as petrified leaves and dinosaur bones, are minuscule and occasionally just show patterns of some of the carbon, sulfur, or iron that was left behind by species that existed billions of years ago, are only chemicals, little signs of life carved into old rock that yet convey a narrative. One of the most astounding findings in this discipline, as magnificent as any epic of kings and empires, comes from scientists discovered a piece of granite in Western Australia that is more than 3.5 billion years old. Discovered what seemed to be the preserved remains of microbiological life trapped in old hydrothermal vent systems, were creatures that lived well below the surface, utilizing chemical energy from the Earth's surface rather than sunbathing on the surface. Interior to survive, which begs the important question of how life could have started. There's a chance that scientists are beginning to believe that the early Earth was a chaotic place, meteor blasted, volcanically active, and devoid of a protective ozone layer. The surface, particularly throughout the first billion years of the planet's existence, it wasn't exactly hospitable, but underground that was under the surface. However, there were chemical gradients, lower radiation levels, and a more stable temperature. Since energy supplies were basically plentiful, it's probable that life didn't arise in shallow waters, as previously believed, but instead started in the crust, where mineral and rock fissures provided protection. Pores gradually changing and growing higher as the surface got more deep. Life endures in locations unaffected by surface events, even forgiveness. Huge asteroid strike, no issue, Ice Age still warms this area. Then a solar flare, microbes 4 kilometers below the surface won't even notice if that destroys satellites. Because of this type of biological isolation, certain microbial lineages may have been developing on their own for hundreds of years, millions, or even billions away from ecosystems on the surface. Even more astounding is the apparent age of some of these biological systems found in Canadian and South African mines. Researchers have discovered ancient water fluid confined in rock fissures that have been isolated from the surface for hundreds of discovered microbial colonies in these waters that seem to have existed continuously for millions of years. Isolation that produces energy in the dark by feeding on hydrogen and sulfate, similar to microscopic biochemical engines. These microorganisms haven't always seen the sun. May have existed from the first days of the sun, before the first fish squirmed through the oceans, when life on the surface was still learning how to grow limbs. Multicellular organisms were there. And it's not just the ancient bacteria found in rocks act as time capsules. By examining isotope ratios and mineral scientists can follow the molecular traces of life that date back billions of years, because two inclusions, even when the patterns that creatures left in the rock, such as boflum textures, elemental imbalances, or imprisoned there, where geology and biology kind of converge. Gases can show that life once wriggled or metabolized. Perhaps the most wonderful thing about scientific poetry is that the stone tells the story. We only need to learn how to interpret it. Concerning the deep biosphere is its consistency. It's not ostentatious. Change quickly as surface ecosystems fluctuate in response to changes in the climate. Despite extinctions and evolutionary explosions, the deep biosphere simply endures in slow motion, with a sort of patience that goes against our typical sense of hurry. Perhaps this slowness is one of its best qualities. Because of their slow rate, subsurface microorganisms are extremely efficient. They don't waste anything, can withstand a lot, and can survive unremarkably. One study discovered that certain subsurface microorganisms might have energy budgets that are just a bit higher than the hypothesized minimum necessary for life. They are functioning at the limit of what biology permits, and they nonetheless flourish as a result. Implies that with such slow rates of reproduction and mutation, evolution down there might have a whole different rhythm, would be minimal, and since natural selection would operate over a longer time span, this might result in a type of molecular conservatism. Is the idea that certain genes or proteins haven't altered much throughout eons. It's similar to biological deep time. Cells that were never exposed to the outside world preserved a live record of the early Earth. As scientists learn more about these ancient ecosystems, new opportunities arise beyond comprehension. Earth's past, but to find out if life began on the planet's interior. Could this be the case elsewhere? For example, Mars may have long since lost its surface water, yet it may still contain if there are liquid reservoirs down below and chemical gradients are visible. It is fair to assume that life may be metabolizing away in its own kind of deep time while lurking there. So the next time someone inquires, you might gently imply that the answer to the question of when life first appeared, or how long life has been flourishing on Earth, is not in the dinosaur remains or early human bones, but in the silent, obstinate microorganisms buried under the crust. Life has been down there for a very long time, witnessing the rise and fall of mountains, the drift of continents, the arrival of creatures, and it remains there, quietly waiting for the next million years in the dark. Because in the deep earth, time is something to settle into, like bedrock, rather than something to run against. Sleep, which is beneath our feet, whispers secrets about other worlds where life exists, in addition to telling us about Earth, can flourish in the darkness. High temperatures and high pressures found deep below the Earth's crust, where light cannot reach, and energy is limited, then why not on other planets or moons? This is not merely an issue of poetics. It's one that has influenced the direction of contemporary astrobiology for many years. As researchers looked for extraterrestrial life, aimed to locate Earth-like circumstances, including warm temperatures, liquid water, and surface, and possibly a comfortable environment with some air that can be breathed. The traditional Goldilocks zone concept, where conditions are when we thought of aliens as slightly greener versions of ourselves relaxing on Earth-like worlds. It made perfect sense. But then we began to gaze within, not necessarily into our souls, but rather into our crust, to see what life was all about. Life in the dark, without sunlight or air, consuming rocks and consuming radiation, prompted us to reevaluate our presumptions. The question now was not whether life could exist in odd settings, but rather why. Let's begin by discussing the surface of Mars. Our rusty neighbor, today, is arid, dry, and chilly, with a thin atmosphere that provides roughly the same level of protection as a damp paper towel. But evidence of former water is etched across Mars, which had rivers, lakes, and possibly even oceans, billions of years ago. Terrain in the shape of sedimentary layers and dried-up rivers, where the most of the water has evaporated now. But there are indications from radar data that some of it might still be underground. According to orbiters, there might be briny subterranean lakes beneath the Martian South Pole. Stay liquid at lower temperatures, and geothermal heat from Mars' subsurface may prevent it from rising if it is buried deep enough. Yes, Mars may have its own subterranean aquifers that are frozen solid. The harsh surface environment, and if bacteria on Earth can survive there, life may exist anywhere there is liquid water. Survive 4 kilometers underground by consuming minerals and hydrogen. There is no reason why Mars couldn't support a similar kind of life. The Martian crust is known to include sulfur compounds, iron-rich minerals, and possibly even pockets of the last one. Methane is particularly intriguing, since on Earth there are geological methods to make methane, of course, but the fact that it's frequently linked to microbial activity, the discovery of cyclical increases in Martian methane has some experts baffled and silent. Europa, one of Jupiter's ice moons, is visible if you're wondering if something might be burping beneath the surface. There, the temperature is about -160. And there is a lot of ice on the surface. Although it's not particularly welcoming, there is an ocean of liquid water beneath that frozen shell. Europa is effectively compressed and stretched by Jupiter's gravity, which is probably kept heated by tidal flexing, warms its interior by friction. Like the ocean floor on Earth, this ocean may be in contact with a rocky mantle. If it is accurate, Europa may include hot places that resemble hydrothermal vents, where heated water rich in Earth's seafloor releases minerals, and these vents are brimming with bacteria, clams, tubeworms, and more. Flourishing in total darkness, using chemosynthesis as fuel. If Europa is comparable, it's easy to see microbiological life clinging to them while concealed behind a kilogram of ice, going about its commerce with no knowledge of the sun's existence. And the same is true of Enceladus, Saturn's little moon. Plumes have been observed, escaping from the frosty surface of a frozen snowball with a heated heart of organic chemicals, dust, and water vapor into space through fissures close to its south pole. These plumes are thought to come from a subterranean sea, and they may contain hydrogen, result of water-rock interactions, or the fundamental components of chemosynthesis could be currently. Missions especially intended to search for signs are being planned by NASA and the European Space Agency. For example, the Europa Clipper is scheduled to launch in the upcoming years and will provide information on life in these far-off oceans. Examine the ice shell ocean and habitability of Europa in great detail. If the Earth's deep biosphere has taught us anything, it is that life can thrive without a sunlit paradise. Only requires time, chemistry, and a tiny shield from cosmic ugliness, which leads to a philosophical change. According to conventional definitions, the habitable zone is a small area surrounding a star, where a planet could sustain liquid water on its surface. But we've had to expand, after realizing that life might flourish beneath. Suddenly, planets and moons that we once thought were too arid or frigid have returned to the game, but not as Earth twins, but as analogues of the interior Earth. Venus is also wrote off as a fiery hellhole, is being examined more closely, and, since its surface is hot enough to melt, some scientists question whether microbiological life may continue to exist in somewhat warmer, subterranean, or even atmospheric regions. Less severe, the likelihood may be low, but the lesson is unmistakable. Never undervalue because life can appear in unexpected places. We now live in a time when the hunt for extraterrestrial life is as much about geology as astronomy. With devices that used to gaze at the stars now looking down, space probes are evolving into interplanetary geologists who are looking for crusts and ice caps rather than great civilizations. However, for lowly microorganisms that exist peacefully in the dark, if we do discover life, if there is a bacterium hidden beneath layers of ice or rock, on a different planet, going about its own thing, it will most likely resemble what we've previously discovered deep within our own world, that is peaceful, resilient, and tenacious without being ostentatious, or speedy, amazing. So keep in mind that the answer may be hidden the next time you gaze at the stars and question whether we are alone. The blueprint for life elsewhere may exist right here, silently beneath our feet, not in space, but in stone. The narrative of how we found life deep beneath the earth isn't one of spectacular discoveries, flourishing where no one dared to investigate. Purpose-built missions or exploration are even messier than that, in the best, like many of science's greatest unexpected discoveries. It started with a little bit of curiosity, and a lot more humans have been drilling into the earth for decades, not to look for life, despite several accidents. However, in the case of gold, oil, and geological inquiries, it turns out that the instruments and tunnels we've utilized to retrieve wealth from the earth have also provided access to the secret world underneath. In fact, a large portion of what we know about mines, oil wells, and scientific boreholes are the sources of the deep biosphere. Underground laboratory. Let's begin with mining, where individuals have consistently gone to great lengths, and for example, South Africa's gold miners reach great depths to extract the Earth's resources. In quest of valuable metal, laborers travel several kilometers down. It's hot, claustrophobic, and hazardous. Studs. But it's also a fantastic chance for science. In these harsh, geologists and microbiologists began to notice unusual water in certain locations, trapped in rock fissures for millions of years. And the water wasn't sterile rather. It was teeming, containing microorganisms, which are microscopic creatures that have never been isolated. For Deceleratus, Ordax viata was found to be alive and thriving in the dark, despite the geological ages. In the Impon gold mine, a single species environment was discovered almost 3 kilometers below the surface. Was not just living but flourishing in a world of rock and radiation. But mining, by consuming hydrogen and sulfate, are not the sole access points to the underground biosphere. The oil and gas sector also excavates the earth to discover fossil fuels, and, in the process of looking for oil, discovered subsurface life. Drilling operations in reservoirs frequently uncover unexpected core samples and fluids from deep beneath. At first, it was believed that some of these fluids contained living things, such as bacteria, which have been discovered to live in oil. These microorganisms are frequently anaerobic, meaning they don't require oxygen, and halophilic, meaning they enjoy salt, found in wells deeper than 2 kilometers. They have adapted to tremendous pressures, high temperatures, and sometimes the hazardous hydrocarbons that we have been drilling, because they are a part of the ecology that has been forming it for millions of years, not merely thriving on crude oil. Years. In certain instances, they even affect the oil's quality by decomposing hydrocarbons, or generating methane as a result. There are scientific expeditions that have chosen to conduct deep drilling as part of their purpose, rather than for financial or material gain. However, one of the most well-known is the Kola super-deep borehole in Russia, which dates back to the Cold War in the 1970s. Delve as deeply as possible into the Earth's crust as part of a period science project, and after almost 20 years, the team arrived at the deepest hole ever bored into solid rock was more than 12 kilometers deep. Yet they didn't locate liquid water, but they didn't find hellfire as some jokes implied. Imprisoned in rock at depths no one had anticipated, and they also experienced very high temperatures, extreme mineral formations, and indications of prehistoric biological activity. Even though circumstances ultimately caused the project to end, it is nevertheless regarded as a scientific milestone and a testament to human perseverance and underground curiosity, while other nations have joined Japan's deep drilling party, Germany's Continental Deep Drilling Program (KTB), and the Chekuhaken mission, utilizing sterile drilling. These programs have penetrated the Earth to investigate geology, earthquakes, and yes, microbiological life. Methods for gathering clean samples that are subsequently examined for DNA chemical evidence of biological activity and isotopes are two major obstacles in drilling into pristine areas that haven't witnessed the effects of human activity can lead to pollution when exploring deep life. Surface over millions of years, and even one surface microbe might skew the results. Therefore, scientists go to tremendous lengths to measures to guarantee the integrity of their samples, including injecting dye markers to trace and flame sterilizing equipment. Working in extremely clean labs and dealing with contamination is like attempting to study a whisper in a tornado. But with enough attention and patience is the indication of rich life, and occasionally the most amazing findings come not even from the drilling itself, but from prehistoric rocks that have been exposed at the surface because to geological upheaval in regions such as Canada's, Greenland, and Western Australia, where some of the planet's oldest rocks can be discovered above ground, displaying biochords and microbial fossils. These hints, which date back billions of years, enable us to reconstruct the history of life beneath the crust when its beginnings, survival, and transformation of the globe have all contributed to a profound understanding of the biosphere as an essential component of the Earth's system and not merely a fascinating phenomenon. Enormous, according to some estimates. It may make up as much as 20% of all biomass on Earth. It is rich in microbes are ancient, possibly one of the earliest forms of life, and have lineages that are unlike anything else on the surface. Our knowledge of life on Earth has changed as a result of our unintentional findings made while drilling and mining. Once believed to be arid rock, it is now discovered to be teeming with hidden ecosystems, suggesting that life needs the Earth, may actually be more alive now that sunshine, oxygen, and surface comfort have been totally appended. The next time you hear about a mine or a deep drilling project, consider more than just the equipment. The minerals, consider the hidden microbial cities and the invisible layers of life. In the depths of our deepest digs, the old water crackles, whispering biological information through the stone. In addition to finding resources, we are also learning about ourselves and the true meaning of life on Earth. When discussing life, it started with a little drill and a little human curiosity, rather than an epiphany. It's simple to think of it as a specialized curiosity beneath the Earth's crust. There is some geological trivia about bacteria, but the reality is much deeper. In addition to being strange and fascinating, deep life is significant, since it is essential to the functioning of our Earth, modifying its chemistry, cycling vital components, and even impacting the air we breathe. And let's start with the fundamentals. The carbon cycle. Implications extend well beyond Earth. The majority of us are aware of the surface forms, where plants take up carbon dioxide, animals exhale it, and although the ocean absorbs a significant amount, a slower and more subdued carbon cycle is occurring far below the surface. In order to take part in this cycle, resident bacteria consume and create carbon-based molecules, frequently in the form of carbon dioxide or methane, specifically methanogens, which are microorganisms that generate living in deep rock formations and sediment layers. They produce methane as a byproduct of their metabolism, which aids in the conversion of methane is created when carbon from rocks and old biological stuff is converted, and it can gradually move upward and escape into the. Conversely, methanotrous microorganisms that eat methane can operate as a sort of biological filter to absorb and digest this gas before it escapes, maintaining this delicate balance. Methane is a potent gas that directly affects the global climate between methane producers and consumers deep down. On short time scales, greenhouse gases are significantly more powerful than carbon dioxide, if drilling or warming may cause more of it to escape from the subterranean biosphere. Hastening climate change, on the other hand, comprehending and maybe utilizing subsurface microorganisms' capacity to absorb or transform methane potentially provide future climate mitigation methods. And the sulfur cycle is another region where profound life exists. Excell's sulfate-reducing bacteria are prevalent in subsurface settings and are essential for the transformation of sulfate is used by these microorganisms as an electron acceptor in their metabolic process that turns it into hydrogen sulfide. This may seem like a small step, but it has an impact on the chemical groundwater composition, the occurrence of specific ore deposits, and the general redox condition of the crust. It resembles microscale microbial terraforming that progressively affects the chemistry of whole geological systems. The deep biosphere also affects the recycling of nutrients, including trace metals, nitrogen, phosphorus, and microbes in deeper geochemical processes are frequently the source of life on the surface. Through gradual, consistent cycling, the deep crust can mobilize these nutrients and make them available to other systems. For instance, microbial populations in basalt can weather rock in the marine crust. Long-term fertilizer release into saltwater, PROMOTEs, surface productivity, and preserves ocean health. Chemistry, therefore, in a way, surface ecosystem health may depend somewhat on, perhaps even more fascinating, is the notion that deep life challenges our very existence, as seen by the silent labor of bacteria far below. We often think of ecosystems as concrete, observable objects, such as coral reefs and rainforests, deserts. But what if one of the biggest ecosystems on Earth is hidden and virtually unreachable from the deep? According to some estimations, the biosphere may equal or even exceed the surface biomass mass. There has been a significant change in our understanding of life on Earth, and it is not merely a footnote in biology. Some species of subsurface microorganisms are already influencing industry and technology through practical applications. Possess enzymes that are useful for biotechnology because they can operate under high pressures and temperatures. Others create molecules having antibacterial or antifungal properties, ranging from industrial chemistry to pharmaceutical development characteristics, and scientists are actively investigating them for possible novel medications as life develops. And it creates some pretty amazing survival tactics in the pressure cooker of the Earth's crust. And some of those strategies potentially aid in the resolution of contemporary issues. And some species of these bacteria may even play a part in environmental remediation, can break down hydrocarbons, lessen harmful metals, or even neutralize radioactive waste. Researchers are looking into how imagine using these organisms in bioremediation, which is a fancy word for using life to clean up environmental messes. It is not science fiction to use a deep living microbe to digest oil spills or stable nuclear waste. The tenacity of Earth's subterranean life serves as an inspiration for these actual fields of study. And there is also the philosophical aspect of it all, is learning that there is a great deal of life out there that moves at its own speed. It is sobering to know that they are not aware of us and are not impacted by surface occurrences. It serves as a reminder that life is not limited to the comfortable periphery. We live in a persistent, flexible, and incredibly diversified place. The biosphere demonstrates that the history of life on Earth is much longer and more extensive than we previously thought, and perhaps even more universal, as life can survive in this environment of heat and pressure inside the Earth. If we discover life on Mars or another planet without sunlight, why not apply the same ideas to other worlds? It might mimic the microorganisms we've already encountered in the crust of some exoplanet or beneath the ice of Europa. Domestically, and that would rank among the most significant scientific discoveries in human history, that in the dark, we are never truly alone. Therefore, even if it doesn't usually make news, the deep biosphere is important. Impacts our ecosystems, our climate, technology, healthcare, and our comprehension of life itself. It's a hidden force that shapes our globe and challenges our perceptions of the world. The next time you look at the ground beneath your feet, keep in mind that it's more than just rock and dirt. It's a living layer that is silent, invisible, yet huge, essential, and patient. We end up back where we started looking, because it might be the planet's heartbeat underground, down with the silent wonder of someone who finally understands what's happening, rather than the apathy of someone walking on stone. Life beneath it. We've traveled slowly and thoughtfully beyond the stony terrain, into the layers of the Earth's crust, limits, and into an environment where life endures without oxygen, sunlight, or hurry, where microorganisms eat minerals, drink hydrogen gas, and calculate the passage of time in millennia. We have encountered fearless adventurers like Dularutis or Daxiator, who have discovered hidden to Jupiter's and Saturn's cold moons. But as always, the most profound findings frequently bring us back to our early, innocent queries. What form of life can endure in complete darkness? How can anything survive with so much heat and pressure? Could something far from Earth be carrying out the answers as to why the same thing is silently flourishing in the shadows of another globe underneath every step we take? We've witnessed realities that aren't just possibilities. Now, I hope this excursion has left you more than merely relaxed. You may fall asleep, but your thoughts will be softer. However, the thought of a massive living ecosystem beneath your bed silently astounded me. You get a reassuring sense of continuity from the oceans and continents beneath your town. Even if you have loved this serene exploration of the bizarre and lovely underbelly of our universe, then life's darkest moments survive. Planet, please think about sharing where you're watching from, liking, and subscribing to Science in Slippers. I always enjoy watching how many minds are traveling together from all over the world, regardless of the time, universe, and if the adventure tonight has kept you slightly more alert than normal, then at least you've gained some knowledge. The Earth is alive, so rest well, fellow adventurer. Now you understand the depth of the fact